Okay, let's go ahead and begin. Today's notes, 11.9, 11.10 today. Okay. 11.9, representation of functions as power series. Let's try to write that better. Okay, so again, let's review what was a power series. Power series was the summation of c sub n of x to the n. Okay, some c sub n. C sub n is just some function of n. Okay, some function of n. Okay, and then n equals 1 to infinity. Okay, so this is a power series. Okay, and so we want a, right, so this would be c naught x to the 0 plus c1 x to the first plus c2 x to the second. Okay, plus dot 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 forever. Okay, so let's look at the following series. Let's look at the series 1 plus x squared plus x cubed plus x to the fourth plus dot dot dot. That's a power series. Okay, plus x to the nth plus dot dot dot. Right. So what would this thing look like? Well, this thing would be just the summation. C sub n would always be 1, right? It would just be always be 1. Okay. And so this would be the summation. Was the summation of x to the nth, n equals, we'll do n minus 1. Okay, otherwise we'd have to start at 0. Well, let's start at 0. Okay, let's start at 0 here. N equals 0. Okay, to the infinity of x to the nth. Okay, equals 1 plus x squared plus x cubed plus x to the fourth. Okay, so what is this thing? This thing itself is a geometric series. Okay, where the common ratio r is x. We just keep multiplying by x to get from the first term to the next term. Okay, so as long as the absolute value of r is less than 1, or in this case, the absolute value of x is less than 1, as long as x is a fraction, then this thing will converge. And so what does this thing converge to? Well, this thing is going to converge, okay, s over 1 minus x. Okay, that's what this thing will converge to. Okay, so the sum of this thing is 1 over 1 minus x, that is equal to 1 plus x squared plus x cubed plus x to the fourth plus dot 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 plus x to the nth plus dot 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 when x is less than 1. The absolute value of x is less than 1. Okay, so for x, absolute value of x less than 1. Okay, so there's a function written as a power series. What's the function? F of x is 1 over 1 minus x. That function can be written as this power series. Okay, that's just that power series. If x is a fraction. Okay, if x is a fraction. Okay, okay, let's do an example here. Okay, express 1 over 1 plus x squared as a power series. Okay, 1 over 1 plus x squared as a power series. How would we express this guy as a power series? Okay, well, let me rewrite this a little bit. Okay, let's rewrite this a little bit. Let's say that this is 1 over 1 plus x squared is equal to 1 over 1 minus negative x squared. Can I rewrite it like that? Sure. Okay, now why am I rewriting it like that? Because this, I think I can say, well, this is like t, right? I could say, I could put a variable in here, t, right? And so I would say, well, 1 over 1 minus t is equal to what? Well, it's equal to 1 plus t squared plus t cubed plus dot 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 forever, right? But what is t? Isn't t equal to negative x squared? So wouldn't we just kind of substitute in negative x squared wherever we see t? Yeah, so this is going to be 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus, let's do another one, negative x squared to the fourth plus dot 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 forever. Okay. Okay, so this thing is going to equal, okay, 1 minus x squared. Now this is a negative x squared squared. The negative here is being squared, so that's plus x to the fourth minus x squared cubed, which is minus x to the sixth, plus x to the eighth. So what is this thing doing? Well, it's just alternating, and it's just going, instead of it going up by a common ratio of, x here, the common ratio is negative x squared. We keep multiplying by negative x squared to get from one to the other. We just multiply by negative x squared times by negative x squared. Right, to go from the first term to the next term, we negative x squared. So our common ratio here is negative x squared. Okay. So as long as that common ratio, okay, as long as that common ratio, is less than, the absolute value is less than -1, then it'll converge. Okay, well, let's express this as a series. Let's express this thing as a series. How would we express this as a series? Well, just think of it as like a geometric series, right? So the summation, right, of negative, okay, negative what? Negative x squared to the nth power. Okay, so this thing is as n equals 0 to infinity. I could just say, hey, we're just going to take negative x to the second, right? So this, if I really wanted to, I could express it a little bit differently. I could say that this is -1 to the nth power, right? Kind of just break it up. the summation n equals 0 to infinity, to infinity of -1 to the nth power times times x squared to the nth power. But a power to a power, you just multiply powers. So I could really write this as this, the alternating series, right? I could write it as an alternating series. Okay, and that would be my series. Okay, I want to express this as a series. Okay. Okay, it doesn't matter if you express your power series written out or as summation. It just happens to be cleaner to write it up as a summation. Okay. Okay. Differentiation and integration, okay, of power series. Oops. Of power series. Okay, so power series. Okay, so here's a theorem. Okay, if the power series what's a power series? N equals 0, okay, of to infinity of c sub n times x minus a to the nth power has radius of convergence, a radius of convergence okay, r greater than 0, then the function, okay, then the function f defined by f of x equals c naught plus c1 x plus c2 x squared plus dot 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 okay. Oh, you know what? I forgot the A's. My bad. There should be A's here. X minus a squared plus dot 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 dot. Okay, is differentiable and therefore continuous. Okay, if the power series function is differentiable and therefore continuous, okay, on the interval a minus the radius of convergence, a plus the radius of convergence, and oh, sorry, should say then. Therefore continues on the interval. Then one f prime of x to c1 plus 2c2 x minus a plus 3c3 x minus a squared plus is equal to the summation of n equals 0 of infinity of n times c sub n times x minus a to the n minus 1. Just says that we can use the power rule of differentiation on every single term. We can differentiate term by term. Okay. Okay, number 2. Okay, number 2 says that we can integrate. So the integral of f of x dx is equal to a constant c, okay, plus, okay, c sub naught okay, c, oh my gosh, no. C sub naught times x minus a, okay, plus c1 over 2 times x minus a squared plus c2 over 3 times x minus a cubed plus ... So this thing is equal to c plus the summation n equals 0 to infinity of c to the n over n plus 1 x minus a to the n plus 1. Okay, and again, it just says that we can integrate term by term, and we can differentiate term by term, and we can integrate term by term. Okay, so which is nice because that's what we're going to do now. We're going to try to integrate and differentiate some of these things. Okay. Good. Okay, number 2. Okay, express 1 over 1 minus x squared as a power series. Okay, express 1 over 1 minus x squared as a power series. Okay, so let's see what we can do here with this thing. Okay. Well, we're gonna take a derivative here. How do I close this stupid thing? Oh, there we go. That's how. There we go. Close it. Yes, please. There. Okay. Okay, let's express this. Well, what did we know? We knew that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the 4th plus ... right? Okay. So what would d dx, okay, what would d dx of, okay, this thing be, the derivative of 1 over 1 minus x be? Well, okay, what would that be? Well, this is going to be d dx of 1 minus 1, or 1 minus x to the negative first power, right? Let's do a bracket there. Okay. Which is going to be, let's take the derivative of this. d dx, oh, let's do the derivative, so we don't need the d dx. Okay, so this is going to be negative 1 times 1 minus x to the negative 2 times, using the chain rule, negative 1. Oh, okay. Well, that's kind of cool. So this is going to be what? The negatives are going to cancel each other out. This is going to be 1 over 1 minus x squared. Ah, okay. So the derivative of the left side here is exactly what I want to end up with. The derivative, so that means I can take the derivative of the right side term by term. So let's do that. What's the derivative of 1? Well, it's 0. It goes away. What's the derivative of x? It's 1. What's the derivative of x squared? It's 2x. What's the derivative of x cubed? It's 3x squared. 4x cubed, 5x to the 4th, 6x to the 5th, plus dot, dot, dot. Okay. It's kind of cool. Okay, so if I wanted to write this as a out in sigma notation, the power series in sigma notation, what would this thing be? 1 over 1 minus x squared is going to be, okay, the summation of n equals 0 to infinity of what? Well, this is going to be n, what do I want? N plus 1 times x to the nth power. Okay, so I think that works. We plug in 0, we get 1. We plug in 1, we get 2x. Yep, this works. So we just want the number in front to be 1 bigger, okay, each time. And so that works. Okay, so there's an identity for you. Okay, so that guy is equal to this. 1 over 1 minus x, the original one, n equals 0 to infinity of x to the nth. Okay, so that guy, okay, is the other identity that we've been working with. Okay, so one is the derivative of the other one. Okay. Yep. Okay, number 3. Number 3, find a power series for a natural log of 1 plus x and its radius of convergence. Its radius of convergence. Okay, find the power series for natural log of 1 plus x and its radius of convergence. Okay, so let's do this. Let's take the derivative of natural log of 1 plus x and let's see what it is. Derivative of natural log of 1 plus x, okay, that is equal to 1 over 1 plus x times 1. Oh, that's interesting. Okay, which is just equal to 1 over 1 plus x, which I could rewrite as 1 over 1 minus negative x, if I really wanted to. Okay, so far so good. Okay, so if integrated both sides, right? If I integrated both sides, right, I would be integrating a power. I could integrate the power series here, right? So I would say that the natural log of 1 plus x is equal to the integral of this power series, okay, 1 over 1 plus x dx. And I could look at the power series for this and then integrate term by term. Okay, and we'd say, oh, okay, well, let's get a power series for this. Okay, so this is going to be, well, what's 1 over 1 minus x? Well, 1 over 1 minus x, 1 over 1 minus x, that was that power series, right? But in this case, instead of just x, we have a negative x, right? We have 1 minus negative x. So this is going to be the integral of 1 plus negative x plus negative x squared plus negative x cubed, right? Plus negative x to the fourth. No, it's inside. Negative x to the fourth plus dot 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 dx, right? Okay. Oops. Where'd my stuff go? There it goes. Okay, so let's integrate this term by term. This is going to be equal to, there's a d, there should be a dx there. Yeah. Okay, come on. Be nice to me. There we go. Okay, so integral of 1 is x. Okay, integral of negative x, that's going to be a minus x x squared over 2, right? This guy is going to be positive because that negative gets squared, and so it's positive. This is just positive x squared. So the integral of x squared is just 1/3 x cubed. Maybe I'll write it like that. 1/2 x squared. This is negative raised to a third power, so that's negative. So again, it's going to be alternating. Negative. Okay, and then this is going to be cubed, so I'm going to raise that to the fourth power. That's 1/4 x to the fourth plus 1/5 x to the fifth minus 1/6 x to the sixth plus, you guys can get the idea here, right? So just it alternates. Okay, so let's try to write this as a series. Okay, so am I going to want to start from 0 or am I going to want to start from 1? We don't have a constant term, so we really don't need to start from 0. Okay. So this is going to be n equals 1 to infinity. Now I have to ask myself, am I starting with a positive or am I starting with a negative? I'm starting with a positive. So if I do alternating, negative, I'm going to want to do an n minus 1 or an n plus 1. Okay, I'll go with an n minus 1 in this case. Okay, but I just want to make sure that when I plug in my 1, that this thing becomes positive, and I start on the right sign. Okay. The next one is just x to the nth, right? I mean, that's pretty easy. Over, okay, over what? Over n. Right? It's just divided by n. That's where we're getting the denominator. Think of this as divided by 1, right? So 1, 2, 3, 4. The power and the denominator are the same. So divided by n. And that is our integral, okay, plus, that's our summation, right? So when we integrate, there is a plus c, unfortunately, right? If we were to integrate this, there would be a plus c out here, okay, plus some constant c, okay. However, if we want to find out what c is, right, couldn't we just let x be equal to 0? Does that make sense? If I ended up with a c plus here, this thing here, then I could just let x be 0, and that would give me my c, right? Because every other term. So let's let x equals 0, and let's try to figure out what c is. Let's try to solve for c. Well, we integrated, right? We integrated, so we should end up with a plus constant. Okay, but let's let x equal 0 on both sides of this. So natural log of 1 plus 0 is equal to c plus 0 minus 1/2 0 squared plus 1/3, right? So you can see that all of these are going to get wiped out. But what is the natural log of 1 plus 0? Well, isn't that just the natural log of 1? And what's the natural log of 1? Well, the natural log of 1 is 0. So what does this tell me? It tells me that my constant had to be 0. Oh, well, that's nice. Okay, and so our constant goes away. And so this thing is just n equals 1 to infinity of negative 1 to the n minus 1, x to the n, all over n. Okay. And that's the power series for that one. Okay, so that's the natural log of 1 plus x is equal to that power series there. Okay, so that's another identity. Okay, another identity. Okay, it did ask us for the radius of convergence on this thing. Let's see what that means. Okay, so the radius of convergence. Okay. Okay. So radius of convergence 4. Okay. What do we have here? We had we were working with the integral of 1 over 1 plus x, right? Dx is equal to natural log of 1 plus x, right? So we want to think about, okay, well, what would be the radius of convergence? Well, this is 1 over 1 minus negative x. So r in this case would equal negative x. So I would want the absolute value of negative x to be less than or equal to 1, I think. I think it's a hard less than. Yeah, because you usually get 1 minus 1, and we don't want that. Yeah, it's a hard inequality. Okay, so the absolute, well, what's the absolute value of x, negative x? Well, that's just that's just going to always make this thing positive. Okay, so that's the same as the absolute value of x. Okay, because I could think of this as the absolute value of negative 1 times the absolute value of x, right? Okay, and the absolute value of negative 1 is 1. So that kind of goes away. Okay, so this is the absolute value of x is less than 1. Okay, so the radius of convergence, okay, what we would call r, okay, is equal to 1. Now, why? Why is this equal to 1? Because I could say that x, okay, how can I state this? X is between 1 and negative 1, right? Negative 1 is less than x, which is less than 1. So x has to be between 1 and negative 1. So 1 and negative 1. And so if we think of this as a radius, a radii, okay, x can live anywhere between 1 and negative 1. So what's the radius of convergence? The radius of convergence is 1. That makes sense. Okay, last example in 11.9. Okay, number 4. Okay, find a power series. Find a power series. Okay, for f of x is equal to inverse tangent of x. Oh, okay, inverse tangent of x. Okay, so let's think about this for a second. Let's go back to our trig sub days, right? Chapter 7, our trig sub days. And I know that the inverse tangent of x is related to 1 over 1 plus x squared. Okay, I know that. It's 1 plus x squared. Okay, so it's somehow related. How are those two related? Does anybody remember? Remember how inverse tangent is related to 1 over 1 plus 1 plus x squared? Yeah, well, isn't the integral of 1 over 1 plus x squared equal to inverse, isn't the integral of this dx equal to that? Does that make sense? You guys remember that? I sure hope so. Okay, you're gonna need that for the final. Okay, so know that. Okay, inverse tangent of x is equal to that. Okay, and so we're going to get 1 over 1 plus x squared. 1 over 1 plus x squared is the same as 1 over 1 minus what? Minus a negative x squared. Okay. That's cool. Okay, it's the same as 1 minus a negative x squared, right? So what was the power series for 1 over 1 minus? Again, we're gonna call this t, right? But we already did this, didn't we? Wait, this is I'm remembering that we did this back in, I think it was example like 1 or something. I don't know. Was this? Didn't we? Yes, we did. See, we set ourselves up for this. Number 1, express this as a power series, right? So what is the power series for this thing? It looks like this, right? That's kind of cool. So 1 over 1 plus x squared is equal to that power series there. Oh, okay. So from number 1, we can just borrow that. We don't have to do the whole thing over again. Okay, why waste our time? Okay, so this is equal to, okay, 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th plus dot, 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 right? And what do we want to do? We want to take the integral of this thing, dx, because that's going to give me, integral of this thing, dx, that's going to give me my inverse tangent, right? That's the inverse tangent. Pretty slick the way that this works. Okay, dx. Tell us how you really feel. Okay, so 1 minus x squared plus x to the 4th plus minus x 6th plus x to the 8th, blah, blah, blah. Again, we're going to integrate this thing. We're going to get a c plus x. We're going to raise this to the first part. This is minus 1/3 x cubed plus 1/5. These are going to alternate. 1/5 x to the 5th minus 1/7 x to the 7th plus 1/9 x to the 9th plus, you get the idea, right? Okay. Okay, so let's see. Let's see what happens here if I plug in 0 to solve for c. What's the inverse tangent of 0? Well, what is the angle whose tangent is 0? What is the angle whose tangent is 0? Well, it's 0. So 0 is equal to c, because I just plug everything in for 0 for x, right? So c is equal to 0, so I can get rid of my c. Okay, so the inverse tangent of x is equal to this power series. X minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th. It's kind of cool. Okay, plus 1/9 x to the 9th plus, or the next one should be a minus. Okay, minus dot dot dot. Okay, so now let's write this in summation notation. Okay, on our Dalmatian plantation. I don't know why I say these things. Okay, because it's from a movie. It's actually the first movie I ever saw in the theater in my entire life was 101 Dalmatians. I do miss the theater. At some point, it will. I'm hoping that our society can maybe create like bubble suits so that I can actually go back to the theater someday. Because I really do miss going to the movies, but I don't miss it so much that I would want to die alone in a hospital bed of COVID-19. So there is that out there as well. But I do miss it. I miss the theaters. Okay, what are we going on? Like month 6 of this thing? It's going to be a year, at least. What happens if they never find a vaccine? I guess I shouldn't say that. That's going to get everybody depressed. But yeah. Anyway, it's a thought that has been going through my mind lately. What if you can't? What if it's like the common cold, and what then? Anyway, okay, that's a philosophical discussion for another day, I suppose. Okay, so let's try to figure out, well, what's the summation of this thing going to be? Okay, well, it looks. Let's do 1/1 to the 1. Okay, if that's okay with you guys, 1/1 to the 1. Okay, I might even rewrite it as x to the 1/1 minus x to the 3/3 plus x to the 5/5 minus x to the 7/7 plus x to the 9/9, right? Okay. Cool. Okay, so notice that we have some odds here. How do we get odd values in a series? Well, it's really easy. Okay, it's just 2n. Okay, plus 1 if you start from 0. If n is equal to 0, if you're starting from n equals 0, then it's just 2n plus 1. But that gives us odd. This is called the odd number generator. If you start from 1, then the odd number generator is 2n minus 1. That's called the odd number generator. That'll generate odd numbers for you. Okay, well, we're going to start from 0. So I just want some odd numbers here. Well, okay, so let's start from 0. N equals 0 to infinity. We want this thing to alternate sign. So I'm going to go -1 to the n minus 1. Okay, maybe I'll, is that right? No, we want to start at 0. So no, so it's just an n. It's just n. Yeah, we're starting at 0 this time. So we just do n, yeah. Okay, -1 to the n over x to the 2n. If we're starting at 0, then we will want 1. So this is 2n plus 1 all over the same thing in the bottom. This is 2n plus 1. Oh, that's it. Easy. Okay, that equals your inverse tangent of x. Okay. what's the radius of convergence of this thing? Well, we have 1 over 1 minus negative x squared, right? So we would say that this thing, negative x squared, is our r. Okay, absolute value of r is less than 1. Okay, so negative x squared is less than 1. So x squared is less than 1. Take the square root of both sides. Okay, and if I square root the absolute value of an x squared, that's the same thing as the absolute value of x. So this is the absolute value of x. I could just bring the squared outside the absolute value because it's not going to do anything. It's going to keep the same result. But this is 1, and so we get the same thing. R is equal 1. The radius of convergence is 1. Okay, 1 is done. Okay, so next. Oh, question? There's a question on the field. So on the test, we will have this type of questions. Sure. Yes. The exact type of question, you're going to need to know how to generate a power series using integration and differentiation. That's all I'll say. Okay, I mean, we just spent an hour on this, so yeah, there's a good chance that you're going to get at least one question like this. Does that make sense? Okay, that's all 11.9. Let's move on to 11.10. Oh, you're very welcome, Patty. So, does anybody go does anybody go to school outside of California? Does anybody go to school outside of California? Or is everybody pretty much in California? Okay. So, is every single campus, is campus housing, this is what I want to know, is campus housing shut down for the next year on every single campus? Has anybody heard anything? I don't know. Probably not. Is anybody going back to campus in the fall? I'll take that as a no from everybody. My sister goes back to campus in the fall, but not me, and we're both in California. What campus does your sister go to? Oh, lab, yes, labs are in person. Okay, yes, yes, labs are in person. She goes to Simpson College up in Reading. I have a friend who graduated from Simpson College. What a small world. Okay. He ended up being a pastor at one of the churches in the area where I grew up. So, but I don't know. Like, I was like, why do you go to college out there? And I'm like, I thought, I don't remember what his reasoning was, but he was basically having college with Smokey the Bear, I think. So that was, I think maybe he wanted to do forestry or something. I don't know, but why does your sister go to Simpson? Jean, does she have a major? She's taking up nursing. Oh, okay. Well, that's good. Yeah, it's a good nursing teaching, like Smokey the Bear type of. Another one is UC Santa Cruz. That's Smokey the Bear. Like, has anybody ever been on the campus of UC Santa Cruz? It's basically it's extremely beautiful, but you're basically going to school with Smokey the Bear. So it's like going away to summer camp for 4 years. So it's pretty cool. And then right down the street is the beach. So you have the mountains, the forest, and the beach right there. It's kind of amazing place. But I didn't want to go there because I was like, dude, living in a cabin with Smokey the Bear for 4 years, not for me. It's for other people. But it was very earthy. Okay, just like Humboldt State, very earthy place, but wasn't for me. But to each his own, right? Okay, so 11.10 is Taylor and Maclaurin series. It's Mac like MacIver. Okay, Maclaurin series. Let's talk about Taylor and Maclaurin series. Okay. Okay, so Taylor and Maclaurin series, how do we get, this is how we get power series for really cool functions, actually. Okay. We take the Maclaurin series and get some really cool functions. Okay. Let's define what a Taylor series is and a Maclaurin series. Okay. Theorem. Okay, if F has a power series, F has a power series representation, okay, at A, comma, that is if f of x equals n equals 0 to infinity of c sub n x minus a to the nth with a radius of convergence x minus a absolute value is less than r. Okay, then its coefficients, these c sub n's, are given by this formula, are given by the formula c sub n is equal to the nth derivative of the function, okay, evaluated at a over n factorial. Oh, kind of cool. Okay, so f sub n is the nth derivative of f at a. Okay, so this is, if you haven't seen that notation, f sub f to the nth power in parentheses is nth derivative. Okay, and that would be evaluated at a. Okay. Okay, so the summation n equals 0 to infinity, okay, n equals 0 to infinity of c sub n of x minus a to the nth, okay, is equal to, okay, f of a, okay, all over 0 factorial. That's the first coefficient, right? C sub 0. Okay, so maybe I'll write this out first. So c sub 0 plus c sub 1x plus c sub 2 x2 plus c sub x squared, sorry. Oh, these are minus a's. I'm messing up all over the place. Okay, plus c sub 2 times x minus a squared plus dot dot dot, right? Okay, so this is equal to, okay, what are the coefficients going to be here? Well, they're going to be f of a over 1 factorial. Okay, that's the zeroth over 0, sorry, 0 factorial. This is the 0th derivative, is just the function, right? 0th derivative, okay, is just a function. And then x minus a to the 0th power is just 1, okay, plus this is going to be the first derivative, right, over 1 factorial times x minus a, plus this is the second derivative over 2 factorial times x minus a squared plus dot dot dot. Okay, we can clean this up a little bit in saying that this is just f of a plus f prime of a times x minus a plus, I mean, I could still put this over 1 factorial, it doesn't matter. Okay, f double prime of a over 2 factorial, just to make sure you know there's a pattern here. Okay, times x minus a squared plus dot dot dot. Okay, and what we call this is we call this a Taylor series. Okay, this is a Taylor series that follows this pattern. Okay, if it looks like this, it's called a Taylor series. It's a power series, but it's a Taylor series centered at A. Okay, it's a Taylor series centered at A. So the Taylor series, okay, the Taylor series, capital T, Taylor series, okay, of the function f, of the function f centered at A is, okay, the summation of n equals 0 to infinity of f to the nth derivative of A, the nth derivative of f over n factorial times x minus a to the nth power. That's the Taylor series. Okay, and what did we just see? We saw that that equals the thing above, the thing right above it. So, right, so Taylor series, okay, is equal to the summation of n equals 0 to infinity of the nth derivative of a over n factorial x minus a to the nth, which is equal to, what do we see? We saw it was f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a. I'll make this a little bit smaller and put more terms in here. Okay, x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus dot 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 forever. Okay, so that's the Taylor series. Okay, that's the Taylor series. Okay, now what we do for convenience, okay, for convenience, we let a be equal to 0. Okay, if a equals 0, then the series is called a Maclaurin series. Maclaurin. Okay, not to be confused with Lauren, which is a very fast car. Okay, different spelling. Okay, then the series is called Maclaurin. Okay, called a Maclaurin series. And it becomes what? Well, it becomes the following, the summation of n equals 0 of to infinity of f to the nth derivative at 0, okay, over n factorial x to the nth. Okay, so we're just centering it around 0. So this becomes f of 0 plus f prime of 0 times x, okay, plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 out of the way, of 0 over 3 factorial x cubed plus ... You get the idea, right? Okay, so that's, come on, behave. There we go. Move up. There you go. Okay. Come on. Come on, come on, come on, come on. Come on, come on, come on, come on, come on. Come on, come on, come on, come on, come on. Valilio. Come on, let's go. Come on, let's go. Come on. Move. 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 Move up. Move your bad self up. Okay, whatever. I'm gonna go like this. Try to be smarter than the average bear. Okay. How is the new computer? It's coming tomorrow. It's been coming in stages. Oh, is this the new? Yeah, tomorrow, exactly. Yeah, tomorrow. It's coming tomorrow. So, yeah. Which doesn't help you guys much because, yeah, because it's the end of the course. But hopefully it will be helpful for the 3 courses that I'm teaching in the fall. So that'll be good. But it's been coming in stages. I have a new monitor I'm working on right now. And then the keyboard came today. So every day I get something to open. It's like Hanukkah, you know, like 8 crazy nights of presents, but it's like 3 crazy days of opening up my computer. So yeah. So, and then every time, my kids think I'm crazy because I'm like, oh, come, and I'm gonna open up another box, and then I always do this. I got a keyboard. So, and then they're like, Dad, you go away. Okay, just go away. Okay, and go back online and play Destiny 2 with your nerd friends, and leave us alone. I'm like, okay, fine. So I'm gonna go shoot some aliens in the corner because none of my kids will talk to me because they're much cooler than me. They're much more popular than I ever was in high school, which I guess is a good thing. It's a benefit. I didn't really talk to anybody in high school, so but yeah. Anyway, so I did my senior year. My senior year, I actually talked to a few people, but it took me 4 years, right? Iron Banner this week for I thought that was coming out in September. No? Yeah. Yeah. Oh, it started yesterday. Is that season, what are we at, like season 7 now? Is it a new season? I'll have to check that out. Thank you, Victor. I've been playing my Paper Mario actually for the last 2 weeks, so I haven't really noticed. So Paper Mario, that's a good game. If you have a Switch, Paper Mario, I'm down with that. I thought it was stupid to begin with, but it's growing on me. So, okay. Okay, sounds good. Well, I know what I'm doing this weekend. Playing Destiny. That's what I'm doing. Okay. Okay, number 1. Let's find the Maclaurin series for e to the x. Okay, so number 1 here. Find the Maclaurin series for e to the x. Okay, so this is how we generate power series. Okay, this is a power series generator, right? Power series generator. Okay, so e to the x should be equal to, should be equal to, the summation of n equals 0 to infinity of f to the nth derivative of 0 over n factorial x to the nth. Okay, so what does this mean? It means it's going to be f of 0 or e to the 0, right? So what's the derivative of e to the x? Well, isn't that just e to the x? Isn't the derivative of e to the x e to the x, and we just keep taking derivatives of e to the x and it's e to the x? Okay, yeah. So this is going to be the original function evaluated at 0 plus the derivative evaluated 0 to the x, okay, plus the derivative evaluated at 0 of that, the second derivative, which is the same thing, evaluated at 0, over 2 factorial x squared plus e to the 0 over 3 factorial x cubed plus, okay, and so what is this? This equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. Hopefully you begin to see a pattern here, right? So what is this? This is just x to the nth over n factorial, right? So this is just equal to the sum of x to the nth over n factorial. Well, that's kind of cool. Of n equals 0 to infinity is equal to e to the x. There's our power series. We just generated a power series. Okay, so we can do this for any function now. Any function we could generate the power series for. Well, that's kind of cool. I mean, that's very powerful. If we wanted a power series for a function, we can just plug this in, take our derivatives, and evaluate. Now, sometimes the derivatives get really, really mangly and complicated, but it's all good. Okay. So if we let x equal 1, we would get e to the 1 is equal to 1 plus 1 plus 1 over 2 factorial, which is 2, plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120, plus 1 over 6 factorial, which is 720, plus ... If I put this into a calculator, okay, real quick. Okay, let's see what we're getting here. This becomes clear. 1 plus 1 plus 0.5 plus 1/6 plus 1/24 plus 1 1/20 plus 1/720. And what do we get? I get this. I get this for the first, what is it? 1, 2, 3, 4, 5, 6, 7 terms, right? For the first 7 terms, okay, or I can say that S sub 7 of this series, okay, the partial sum is 2.718, and it will be O5s forever, okay? And so if we continue to add successive terms, okay, if we continue to add successive terms, it would just only get closer and closer, okay, to the natural exponent, which is 2.718281828, okay, 45, 90, 45. Okay, and so it works. It works out. Nice. Okay, very cool. Okay. Okay, let's see what else we got here. Okay, T sub n of x is equal to the summation, okay, of I equals 0 to n, okay, of f to the ith derivative of a all over, okay, I factorial, okay, x minus a to the ith degree, okay, is equal to f evaluated at a plus f prime of a times x minus n. This is our Taylor polynomial, right? This is our Taylor series. This is our Taylor series. Okay. Okay, plus, okay, but it's only going to go up to n. N, we're going to stop at n. Okay, it's not going on forever. It's stopping at n. So this is f double prime of a over 2 factorial. Okay, x minus a squared plus dot dot dot, and it ends. It ends at the nth derivative of a over n factorial x minus a to the nth degree. It stops. And what this is called, okay, when I only go up a certain amount, or we take our partial sums up to n, okay, you can think of this as S sub n, okay? It's our partial sum of our Taylor series. We call this, okay, T sub n sub x is called a Taylor polynomial. Maclaurin has no polynomial because it's just a Taylor polynomial centered at 0. So Taylor is called a Taylor polynomial. Okay, it's a Taylor polynomial. Okay, think of it as the nth partial sum of the series. Okay. Okay, so R sub n of x is called the remainder, okay, the remainder okay, of the Taylor series. Remainder of the Taylor series. Right? Taylor series. Think of the Taylor series, the whole thing, as S, right? And so we would say that so the function, the whole function, right? So f of x is the Taylor series. F of x is equal to the Taylor series. Okay, equals the whole thing. The whole thing. Okay, this is the sum n equals 0 to infinity of Fn of a all over n factorial x minus a to the nth degree. Okay, so that f of x is the whole Taylor series. That's the whole thing. This is, think of it as like the limit, right? This is the sum as we go to infinity, right? It's the whole function. Okay, it's the whole function. So what we can say is we can say that the whole function f of x is equal to, okay, think of this as s, right? S, right? We could think of it as s, the remainder, it's going to be and s is equal to the partial sum plus the remainder. Does that make sense? It's the partial sum plus the remainder. What I would have left to add on. Again, let's go back to our example here, where we had, look at s sub 7, we had this guy, right? And then we had the entire function. Evaluated one is that guy. And so the difference between the two would be the remainder. It would be the error between the actual sum of the function and the value that I got by taking partial sums. So f sub x is equal to, okay, what we're calling s sub n, we're calling t sub n sub x. That's the Taylor polynomial. This is the polynomial plus the remainder, which is a function of x. Okay. Okay, as long, and we can say this, okay, as long as this thing as the remainder gets smaller and smaller. As long as, okay, the limit as n goes to infinity of r sub n of x is equal to 0. Okay, r sub n of x is equal to 0. Okay, so we have a function here, and we have a Taylor series, or a Taylor polynomial, and the remainder. Okay. Okay, let's talk about Taylor's inequality for a second. Okay, so this would be the error. This would be the error, or the extra piece. Okay, that we would want to get. Okay, and this is the original function. Okay, or the original power series. Right, polynomial, which is your partial sum. That's the remainder, or what we would call the error. Okay. Okay, find the Taylor series. Sorry, Taylor's inequality. Let's look at Taylor's inequality here. Okay, if the absolute value of f to the n plus 1 of x, absolute value, is less than or equal to m for x minus a is less than or equal to d. Okay, so the nth derivative of x is less than or equal to m. For x minus a is less than or equal to d. Think of d as like maybe delta. Okay, then the remainder r sub n of x satisfies the inequality absolute value r sub n of x is less than or equal to m over n plus 1 factorial absolute value x minus a n plus 1, okay, to the n plus 1 power. Okay, for x minus a, which is less than or equal to d. Okay, so what the heck does this all mean? Well, we're just saying that there is a difference between the function, how the function behaves, and how the polynomial behaves. Okay, and that this remainder, okay, is going to be bounded. It's going to be bounded by this thing here. Okay, by the next term. It's very similar to what we did before when we said, hey, when we had our alternating series, the next term bounds the error, the remainder. Okay, that's really all that is talking about. Okay. Okay, so let's look at a Taylor series. Okay, let's look at the Taylor series, and we'll talk about maybe the errors and whatever is involved in this. But I want to talk about this Taylor series. Okay, for E of x. Okay, E of x. So let's look at the Taylor series. Let's look at the Taylor series. Okay, because things get really spicy. What's coming up next is basically my favorite part of the entire course. So series. Okay, let's look at the Taylor series for, okay, f of x is equal to e to the x at a equals 2. Okay, so how I got off the page so badly, but that's okay. It's all good. Okay, let's look at the Taylor series of this thing. So e sub x is equal to, okay, f sub a plus f prime of a of x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus dot, 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 dot. Okay, so let's look at the Taylor series here. Okay. Okay, so what's going on? Well, let's look at our derivatives here first. Okay, so if f of x is equal to e to the x, then f prime of x is also e to the x. Okay, and it just keeps going, right? This is the derivatives are itself. That's the property of e to the x, is that it is its own derivative. So what is f of 2, f prime of 2, f triple prime of 2? Aren't they all e to the 2, right? Wouldn't they all be e to the 2? Okay, so e to the x is equal to, okay, e to the x is equal to, okay, f of 2, well, what was f of 2? I'll put that in here. F of 2 plus f prime of 2, x minus 2. Let's put in all the a's. Okay, x minus 2 plus f double prime of 2 over 2 factorial x minus 2 squared plus f triple prime of 2 over 2 factorial times x minus 2 cubed plus dot, 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 dot. Okay. So let's look at the terms, what the terms are doing here for this Taylor series. Okay, so what is f of 2? That's e squared. E squared. That's just the constant. Okay. Plus, what's f prime of 2? That's just e squared. Okay, e squared times x minus 2. Okay. Plus, this is going to be e squared over 2 factorial, which is 2. Okay, x minus 2 squared. Okay. Plus, this is going to be e squared over, oh, this is a 3 factorial, sorry. 3 factorial, which is 6, times x minus 2 cubed, plus dot, dot, dot. Now, here's kind of the cool thing that's happening here, okay, is that if we look at our partial sums here, right? Let's look at our partial sums. What's s sub 1? What's s sub 1? Isn't that just e squared? Okay, which is just a constant. What is e squared approximately? Let's see what e squared is. Let me plug that in my calculator. What happens when I take e and I square it? E squared. I get about 7.38. So we're saying that f of x is equal to 7.38. Okay, that's kind of interesting. Okay, not too good, but it's all good. It's all good. It's all good. Okay, 7.38, right? So 7.38. So let's look at a graph. Okay, let's look at a graph of e to the x. So when x is 0, we're at 1. When x is 1, we're at 2. Okay, maybe I'll make this bigger. Okay, make it really tall. Okay, when x is 1, 2, 3, 4, 5, 6, 7, 8. There we go. I'm gonna go up 8. Okay, got this. Got the idea here. Okay, maybe I'll switch. Maybe I'll switch colors here. No, you don't want to tag anybody. Okay, so at 1, right? At 1, we're there. For e to the x, okay, at 1, we're at 2.78. So that's almost 3. 2.78. At 2, where are we at? We're at 7.38, right? 7.38. So we're getting this curve. Okay, this exponential looks like this. Does that make sense? Exponential. Okay, exponential. Okay, nice. So I'm going to try to connect the dots here as best as I can. So whoosh, whoosh. The sound effects do help. You got to do a little whoosh, whoosh, whooshing, whoosh. There we go. Okay, boom. There's a point. If your graph doesn't go through your points, just make your points bigger. Okay, that's how we cheat when we teach math. Okay, just make your points bigger. So it's all good. Okay, and then you're like, oh look, it actually goes through my points, even though my point is like half the page. Okay, it's the size of half the page. Okay, so everybody see my lovely e to the x here, right? Okay, so here's the deal. Okay, here's the deal. Actually, you know what? I'm going to do this. I'm going to do this in Desmos, but let's do it. Let's do. What does it mean that f of x is equal to 7.38? What does it mean f of x is equal to 7.38? Well, that's just a horizontal line, right? That's a horizontal line. So I'm going to do this in Desmos eventually, but if I wanted a horizontal line, right through here, that would be, okay, my first partial sum. I'm going to call this S sub 1. S sub 1, that's kind of cool. Okay. let's look at, so this was S sub 1. S sub 1 was equal to E squared. S sub 1 is equal to E squared, which is equal to 7 point, what do we say it was? 7.39, we'll call it 7.39. Okay, 7.3. Boom, right there. S sub 1 is, okay, so f of x is equal to S sub 1, which is just that guy. Okay, now what happens? Well, let's look at S sub 2. What shape should S sub 2 be? What shape should S sub 2 be? S sub 2, okay, of x, call this S sub 2 of x, is equal to what? Well, it's E squared times 1 plus x minus 2, which is just E squared times x minus 1. Oh, okay. Okay, so what is this? Isn't this is a line, E squared x minus E squared. Okay, cool. This is a line that has slope E squared and y-intercept E squared. Is that right? Yes, negative E squared. So it has slope E squared and y-intercept negative E squared. So if we go down, okay, to this guy, 1, 2, 3, 4, 5, 6, 7, 8, right? So y-intercept there, okay. I don't want rule lines. I just want a ruler. Maybe it doesn't have a ruler. Maybe this one doesn't have a ruler. Maybe I can find it as an add-on. Anyway, so what's this going to look like? Well, this is going to look like, I can just use some sort of straight edge. I'm going to use my phone, actually, as a straight edge. Let's see if this works. Ooh, don't be moving on me. Okay, don't be moving on me. Okay. Stop. Be nice. Be friendly to me. Okay. Boom. Oh, like right there. Okay. Well, look at that. That is a line that goes through, okay, negative E squared, but has slope of, right, has slope of E squared. Okay, has slope of E squared. Okay, negative E squared, and it has slope of E squared. Right? I think that's how that works. Okay, because, yeah, that works. Because what happens when x is equal to 2? We would get 2 E squareds minus an E squared, which is just an E squared. So 2 comma E squared is a point on my line. Very good. Okay, that's a point on my line. So okay, so the idea here is that this is going to be a linear, so I'm going to call this S2. And now if I add a third term on this, what is the shape of the curve going to be if I add a third term on? If I go to S3 here, what is the shape of the curve going to be? Let me make this red. If I do S3 of x, well, isn't the shape of the curve going to include a squared term, an x squared term, right? So it would be, exactly, thank you, Susan. It would be a parabola, it would be quadratic, right? And so if we include the next one, the next term, this is e squared times, okay, 1 plus x minus 2, okay, plus x minus 2 squared, right? What are we going to get? We're going to get a quadratic, right? A quadratic equation. I don't know what this is going to clean up to, but we could easily find out. This is e squared times, this is x minus 1 plus x squared minus 4x plus 4. Okay, so this is going to be e squared times x squared minus 4x plus x is minus 3x plus 3, right? So something like that. So I could then just redistribute the e squared. So this is e squared x squared minus 3e squared x plus 3e squared. And it's going to be a quadratic. It's going to be a quadratic. And you know what is, when x is 0, okay, when x is 0, this thing is 3e squareds. Okay. Is that a negative or positive? Did I mess this up? Make sure I got this correct. Okay. So e squared over 2. Oh, wait, where'd the 2 go? I messed this up. There should be a 1/2 here. My bad. There should be a 1/2. Okay, it's e squared over 2. So this should be 1/2 x squared, 1/2 x squared, e squared over 2. Okay, 1/2 x squared, and then this should be minus 2x plus 2. Minus 2x plus 2, yeah. Okay, and so then this should be minus 2x plus 1, that's minus x. This is minus x, and then this is plus 1, I think. Yeah, so this becomes, okay, e squared over 2x squared minus e squared x, that's good. Okay, plus e squared. Okay, so think about this for a second. Okay, so again, I just want this thing to make sure that I did this correct. 1/2. Okay, that's x squared minus 4x. Okay, plus 2. Okay, and we've got e, this is x minus 2. Okay, we've got 1, right? 1 plus x minus 2 is x minus 1. That goes to 1. Okay, so, okay. And so, I don't know, I'm going to do this on Desmos. Okay, I'm not going to try to do this by hand, but the idea is that it would be nice if we could do it by hand. Okay, it should work out. That's -1. Yes, it's -1. That's positive 4 divided by 2 is positive 2. That's right. So it's a positive 1. Okay, so that's x squared minus 2x plus x. Plus, okay, let's just call that s sub 3 of x is equal to that. Okay, so this is a quadratic. Okay, it's quadratic. When I plug in 0, okay, I get 0e squared, which is this point here. That's what's messing with my mind there. Okay, but at any rate, okay, let me just use Desmos, okay, to show you what's happening here. Okay, real quick. Let's, because it's gonna hug this thing even better. The more increasing, the more terms that I increase, the better a polynomial representation that we're gonna get of this thing. Okay, we should get, okay, this to get hugged like this. Okay, if we do a cubic, we should get it to look like this. Okay, this would be S3, this should be S4. Okay, if we did a, right, it's just increasingly closer and closer and closer at 2. Okay, at 2, when x is equal to 2. Okay, when x is equal to 2, I should get an increasingly closer and closer and closer and closer approximation to this thing. So let's go to Desmos and see what's going on with this. Okay, because I don't want to get lost in the algebra. Okay, maybe I made an algebra mistake or something, but let's see what the computer says. Okay, so here's Desmos, and we're gonna turn that on. Okay, so what was the first one? The first one was we wanted y, okay, y equals e to the x. Okay, or sorry, e squared. Okay, so y equals e squared. So let's see what that looks like. Looks like that, right? Okay. What was our original function? Our original function was, well, we'll plug that in the end. Okay. What about y equals e squared times, what was this? X minus 1, I think it was. Yeah, x minus 1, x minus 1, not 2, x minus 1. Boom. Okay, there we go. There's that line. Okay, let's do the next one here, which should be y equals, okay, e squared. Okay, so I'm just going to write out the terms this time. E squared, okay, plus, okay, the first derivative, okay, so this is going to be e squared times x minus 2, okay, raised to that's just the first power, okay, plus, and this is going to be e squared over 2, e squared over 2, did you have a comment? Okay, is your screen stopped? No, my screen is not stopped. Is it stopped for you? Yes, okay. Well, let me stop my share, and then I'll try to share my screen again. Okay, is that better? Can you see it? Hopefully, I don't know. Okay, okay, e squared over 2. Yeah, good. Okay, e squared over 2 times, okay, x minus 2 squared, right? X minus 2 squared. Boom. Okay, so that's that parabola there. Okay, that's that parabola there. Where was the, where? Oh, I see why it goes up to, yeah, we had it right. We had it right. We had it right. It just, the vertex was here. I was thinking that it would hug the original shape a little bit better. But what we're gonna see is if we zoom in here, okay, this thing's gonna approximate at at the point 2e2, okay, 2e squared, it's going to hug that line, hug that function increasingly better and better. Okay, so put a label there. Okay, boom. Okay, and now let's do one more where we plug in the next term. I'm gonna copy and paste this thing. Where's my mouse? There it is. Okay, so I'm gonna copy this thing and I'm gonna paste it. Control C, Control V, and then what I'm gonna do with this guy is I am going to add on my third term. And this is going to be a cubic, right? This is going to be a cubic. So this is going to be e squared over 3 factorial, which is 6. So this is e squared, okay, over 6. Oops, wrong slash, over 6. Okay, and then it's x minus 2 cubed. X minus 2 cubed. Okay, so x minus 2 cubed, right? And then that's, look at that. Look, it's a serpentine. Okay, kind of goes like so. Now what we're going to do, I'm going to plug in the original function, okay, which is y equals, this is what we want to approximate. Well, this is kind of like when we did our linear approximation, right? We used you know, Newton's method for linear approximation back in Calc 1, right? So this is the same thing, but we're just increasingly, we're getting increasingly, instead of doing a linear approximation to the function, we're doing a cubic, and then we can do a quartic, and then we can do a quintic, and we can just keep doing these on and on and on. Okay. And getting increasingly closer and closer and closer to the actual curve at 2. Now this is the curve at 2. It's not the curve for any other point. Okay, and I'll show that in a second. So this is y equals e to the x, right? E to the x. Boom. That's e to the x. So was our original, I'm going to try to change the color on our original one. Okay, what was our original? So the first one was just a flat line, not too good of an approximation to the curve at that. Maybe I can make it purple or something. Let me change the color here. No, did I run out of colors? Orange? No, orange is, did I already use orange? Nope, I'm good. Okay, so done. Okay, so that was a really bad approximation to, now the original one, maybe I'll switch these. Okay, maybe I'll make this, the original one, maybe I'll make black. Okay, so there's my e to the x. Okay, so it's the original, what it's approximating. Okay, the line was a little bit better of an approximation. Okay, at this point to the function, to that black function, the line x. I mean, if I want to zoom in here, okay, we can see that the line x was a little bit better of an approximation when we went to so that one was blue, right? That's that blue line right there. That's the approximation that's the linear approximation, what I should be saying. That's the linear approximation, is the blue one here, which you can see is off the mark. There's error. The first one that starts creating error is the linear one here. That's that blue one. And then what's the next one that creates error? What's the next one that creates error? Oh, it's the green one. See how the green one starts diverging from that black line second? Oh, the green one starts getting more error. Not as much as the blue, and certainly not as much as the error from just taking a straight line. That's insane. That'd be bad. Okay, and then what would be the last one here that would what would be the last one that you would think would be diverging from this? And that would be the, let me go back here. Okay. Okay. It would be the red one, right? The red one would be the last one to diverge because it has even more accuracy. Can you see how as I take more and more successive terms of the polynomial, it becomes more and more accurate at that value. It creates a polynomial that is approximating this curve. Okay, and that's the whole idea behind, taking these Taylor polynomials. As we're saying, we can take and turn any function into a polynomial as long as we take successive terms at that value. Okay, it gets increasingly more and more accurate. So again, okay, let me zoom in here. Okay, let's do some zoomage here. Zoom in. So I don't want to lose the forest for the trees here. Okay, but we can see, right? We can see that. Oh, okay. So what was a really good? What was a really bad approximation? It was the just flat line, horizontal line. What was the next best approximation? It was the straight line. It was the linear approximation. And then what's the next best approximation? It was the curved parabolic approximation, right? Okay, and so what I could do is, if I really wanted to be sneaky, is every place that there's a 2, I could put an a, lowercase a, thank you. Okay, and then put a lowercase a here. Okay, a, and I'm gonna, yes, I want to add a slider. I want to add the slider a here. Okay, and the slider a is going to be, we started this slider at 2. Okay, so slider here, we started at 2, so that's where we want to go. Okay, and then again, I'm going to put in a's here for these values. Okay, this is so much easier to do in the classroom. So I honestly feel like teaching behind a screen, I can do it, and I think I'm pretty successful at it. But it's like teaching with one hand tied behind your back. It really is, in a way. It's like, it's a challenge. It's more challenging. But you know what? There's never been a challenge that I have not met head on in my life. And this is going to be no different, except eating tomatoes. That was the only challenge that I was like, you know what? Screw that. I don't want to eat those damn tomatoes. And it's like, get it. My mom, my stepmom, she was a bitch. And no, just a complete bitch. She made me eat tomatoes. And I would like gag on them all the time. The wicked stepmother. She was wicked. She purposefully did not feed me. And this is like ages 5, 6, and 7. She purposely withheld food as a punishment. Now, I have no idea why she didn't go to jail for this. But that's because my parents were all screwed up. And so yeah. But I think out of spite for her, like starving me, I won't eat them. I won't eat the tomatoes because she was a total bitch and starved me as a punishment for my behavior. So yeah. Okay, so see how we got 2 here, and I plugged in all the A's. The A's. This should be an A as well down here. Every time I see a 2, I got to plug in the A values. Okay, and so this is right. And so what would happen if I move this? Did I get all of them? I want to make sure I got all of them. This is squared, right? Squared. Where's the cubic one? Did I lose the cubic one? Is there a cubic? I think I lost it. I accidentally deleted it. Okay, so let's add that one real quick. Let's add that. Go back, go back, go back, go back. Okay, so I want to add this one. Let me copy and paste this guy. Copy, copy and paste. Control C. Okay. Control V. And I want to add to this the 6, right? Add, okay, e to the a, e to the a over 6. And then we want to do x minus, these are all going to be x minus a's. Okay, so I still have a little bit of work to do here. Okay, raised to the 3rd power. Okay, so let's go back in here and let's just, every time we see a 2, we're going to put an a. Every time we see a 2, we're going to put an a. Okay, I think that's good. That's good. I like what I've done there. Okay, every time I see a 2, I put in an a. Every time I see a 2, I put in an a. And I think I'm good there. Okay, this one should be not a 1. This should be, I'm going to delete this. Then I'm going to delete that. I'm going to go back to the original, which was e to the a. E to the a. It's just e to the a. E to the a. E to the a. Okay, boom. Okay, so this should hopefully give us, okay, let me label this the correct color. Okay, so done. Okay, so this should hopefully show us what happens when we choose a different a, right? What happens when we choose a different a? When we choose a different point, right? When we do x minus 1, right? So if I just, what the heck? Will you stop moving all over the freaking place? There you go. Okay, just stay. Okay, so now what I'm going to do is I'm going to use my slider here, and I'm going to slide and say, ooh, look at this. Isn't that beautiful? Look at that. What is happening? Well, we can see that's the linear, right? The linear, does that work? Why is that not working? Did I do it wrong? It should be x minus, oh, yeah, x minus a. Sorry, there should be an a in front of here. X minus a. There should be an a there. I think that will fix it. Maybe. It should be at the point that, I don't know. Okay, it's e to the a times x minus a. It's e to the a times x minus a, right? Times, no, it's e to the a plus e to the a times x minus a. That's what it was. That's why it's not working. Times e to the a times x minus a. X minus a. Parentheses. Okay, there we go. Now we're cooking with gas. So there you can see, look, okay, as I change points, okay, they all hug the exponential at that value. Okay, the black is the exponential, and it's hugging this exponential, and we can see that the red one, which has the most amount of terms, the red one hugs that exponential curve the best. Even if we come down here at, say, let a equal -1, we can see that that red curve is the one that approximates, okay, what's happening at that point the best, right? Does that make sense? Does my whole point here make sense? Does that make sense? That you keep adding more and more terms, you're going to get closer and closer to, yeah, exactly. You're going to get closer and closer to the actual function at that point. And so this is, there you go. And you can see that. Now, you know, 20, 30 years ago, you couldn't, I could not model this for you like this. This is the magic of having computers on your side, okay, with modeling mathematics. You can see these really cool things, okay, in real time, okay. So that's the exponential curve. It just follows the exponential curve, right? Oh, look at that. Okay, and the red one will always be the closest approximation. Okay, boom, nice. Okay, enough of that. Okay, so let's talk about the Maclaurin. Let's talk about the Maclaurin series for sine and cosine. Okay, let's talk about the Maclaurin series for sine and cosine. Cancel. Okay, let me go back to sharing my screen. Okay, screen share. Okay, so here's this guy. Okay. Okay. So we want to find, okay, number 3 here. Okay, find the Maclaurin series for, okay, find the Maclaurin series for sine of x, for sine x, okay. So we want to know that sine x is equal to, okay, f of 0 plus f prime of 0 times x minus 0, so that's just x, plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus f to the fourth derivative of 4 factorial x to the fourth plus dot dot dot. Okay. So we've got to find our derivatives here. Okay. This is just going to be the sine of 0, right? Okay. What's the derivative of sine? Well, the derivative of sine is cosine of 0, right, times x. Okay. Plus, okay, so let's start taking some of these derivatives. Okay, so so our original function f of x is equal to sine x. If I take the first derivative of this, that becomes cosine x. If I take the second derivative, that becomes negative sine x. If I take the third derivative, that becomes negative cosine x. And if I take the fourth derivative, I'm all the way back to sine x again. Okay, does that make sense? Okay, so this was just going to cycle through every 4 derivatives. Okay, every fourth derivative, I'm going to go back to my original one. Okay, so this was negative sine of 0 over 2 factorial x squared plus negative cosine of 0 over 3 factorial x cubed plus all the way back to sine of x, or sine of 0, over 4 factorial x to the fourth plus dot dot dot. Okay, so what is the sine of 0? Well, the sine of 0 is 0. So this becomes 0. What's the cosine of 0? 1. This becomes 0 times 1x, okay, plus, this is negative 0, so that whole thing goes to 0, 0, minus 1 over 3 factorial, or I'm going to put x cubed over 3 factorial, plus, okay, the sine of 0, that's again 0, okay, and then I'm going to go, I'll do the next one here. The next one would be the cosine of 5x to the fourth up x to the fifth over 5 factorial. So this would be a plus x to the fifth over 5 factorial. Well, this is going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And so hopefully you can see the pattern. Okay, it is alternating, and it's the odd values here. Okay, it's the odd factorials. It's the odd powers and the odd factorials. Okay, this is 9. So what is this going to be equal to? Well, it's the sum of n equals, I could say, what do I want to start at? Do I want to start at 1 or 0 for this? Maybe I'll start at 0 just to keep things consistent. This is going to be negative 1 to the nth power because it's alternating. And then it's x to the 2n plus 1 all over 2n plus 1. Remember, that's how we got our odds before. 2n plus 1, sorry, this is factorial. Okay, so that is sine x right there. Sine x. Okay. Okay, what about cosine x? Well, we're going to cheat for cosine x because cosine x is equal to the derivative of sine x. And we said that we could take the derivative of our power series. Okay, the derivative of power series okay, and so let's take the derivative of each of these guys term by term. Okay, so the derivative of x to the first over 1 factorial minus x to the third over 3 factorial minus x to the fifth over 5. Oh, come back. 5 factorial plus x, sorry, that's a plus, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. 9 factorial, right? Whoa. Okay. Okay, plus dot, 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 right? So let's take the derivative of this. Let's take the derivative of this. Okay, so the derivative, okay, the derivative of each of these things. Okay, so what's the derivative of x? Well, isn't that just 1? What's the derivative of x cubed? That's minus 3x squared over 3 factorial. Okay, plus, this is going to be 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial plus dot, 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 right? That's the derivative of this thing. So the derivative of sine x, right, is equal to this thing. Well, what is this? Let's clean this up. Well, what's 3 factorial? Isn't 3 factorial 3 times 2 times 1? So wouldn't the 3 on top cancel with the 3 on the bottom? Yeah, and so that actually just reduces it by 1 factorial. So this is 1 minus x squared over 2 factorial plus, okay, x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. Okay, plus dot, dot, dot. Oh, that's kind of cool because those are the even powers, right? You can think of 1 as x to the 0 over 0 factorial. Think of 1 as that, right? Then this is the even powers and not the odd powers. Oh, okay, so the cosine of x is then equal to the sum of n equals 0 to infinity of -1 to the nth power, right? Times x to the 2n over 2n factorial. Pretty cool. Pretty cool, right? Pretty cool. Okay. Makes sense? Okay. Okay, so to sum this up, okay, what was the sine of x? The sine of x was the odds. So think of this as x over 1 factorial minus, or just x, right? I mean, think of it as x minus, okay, x cubed. It always starts with a positive. X cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Okay, x to the 9th over 9 factorial. Okay. Right. Okay, x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus dot, 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 right? Cosine of x. Cosine of x was 1, okay, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 7 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial plus dot, 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 dot. This is going to be very important in a minute to know this. Okay. What just happened to my line? Sorry. Come back, Mr. Line. Isn't it x to 6 over 6 factorial? Oh, yeah. Sorry, my bad. Thank you. Yes. Okay. Okay, so come on, come back. There we go. Okay, so now let's see the really cool part. Like, this is my favorite part of Calc 2. Okay, my favorite part. This is my favorite formula. It really is one of my favorite formulas of all time. Okay, it's really, I used to call it proof of the existence of God, but I can't get away with that anymore. So a student complained one day that I said the word God in class, and he's like, I'm an atheist and you should not be saying God in class ever. I'm like, okay, fine, that's fine. But so now I just say that I used to call this the proof of the existence of God, formerly known as, formerly known as the artist Prince. This is formerly known as the proof of the existence of God. Okay, so that's how I get away with it. I just quote. I do the quote of myself. I'm just quoting. I'm quoting that. I'm not espousing any theology here. I'm just air quotes. Okay, quoting. Okay, so let's talk about Euler's theorem. Euler was probably he was probably the best mathematician of all time in all of history. Euler, that's where we get this little E from. That's Euler came up with the E for Euler. Euler's constant was the natural exponent. Okay, that's Euler's. Euler, everything in mathematics. Okay, he was just amazing. Formula. Let's talk about Euler's formula. Okay, Euler's formula. Okay, so let's look at e to the x here. E to the x. What is e to the x? It's 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus, you get the idea, right? Are we good? We good on this? Actually, let's go out a few more terms. Okay, I really want to do this justice. Okay, this is x to the 7th over 7 factorial plus x to the 8th over 8 factorial plus x to the 9th over 9 factorial plus dot, 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 dot. Okay, does that make sense? So far, so good? That's, okay, this is not Euler's formula. This is just the power series for the natural exponent. Okay, we're going to derive Euler's formula in a minute. Okay, this is not Euler's formula. This is just a power series. Okay, we've already derived this. We're already good with this. Okay, we're good with this. Okay, we derived, this is the Maclaurin series. This is the Maclaurin series. Maclaurin. This is the Maclaurin series for e to the x. Okay, that's just the Maclaurin series for e to the x. Okay, we're good. Okay, so now what I'm going to do is I'm going to say, well, what happens if I do e to the ix? E to the ix, in the imaginary number I here, what happens? Well, this becomes I1 plus ix plus ix squared over 2 factorial plus ix, okay, cubed over 3 factorial plus ix to the 4th over 4 factorial plus ix to the 5th over 5 factorial plus ix to the 6th over 6 factorial plus ix to the 7th over 7 factorial plus ix to the 8 over 8 factorial plus ix to the 9th over 9 factorial plus dot, dot, dot. Okay, so far so good? Okay, so let's take these powers of i's and see what this is. This is 1 plus ix. Well, what's I squared? What's I squared? Isn't that -1? Right? So this would be negative x squared over 2 factorial. Oh, okay. 2 factorial. Okay, and then plus, this is I cubed. Does anybody know what I cubed is? What's I cubed? If you were to simplify I cubed, what's I cubed? -1? No, not -1. I cubed is -1 times I. Negative I, there we go. Thank you. Okay, negative I, right? So this is going to be, what did I do? Did I do anything wrong here? This is negative, yeah, negative I. So this is minus, come on, erase. This is minus I x over 3 factorial, x cubed over 3 factorial, right? Okay, and so then we're going to go plus I to the 4th. Well, what's I to the 4th? I to the 4th is 1, right? So I to the 4th is 1. So this is just x to the 4th over 4 factorial, right? Plus, this is going to be I to the 5th. Well, it is the pattern, you know, continues. I to the 5th is just I, right? It's just I. So this is I x to the 5th over 5 factorial. This is plus negative, this is going to be a -1. So this is minus x to the 6th over 6 factorial. This is going to be plus, sorry, no, this is minus I minus I x to the 7th over 7 factorial. Okay, this is 8th. The 8th power is going to be, what is that? The 8th power, oh, that's just 1. That's just 1. So this is going to be plus x to the 8th over 8 factorial. And then again, it starts over, right? Every fourth one, it starts the pattern over again. It goes positive, negative, negative, positive, positive, negative, negative, positive. The next one's a negative, right? No, the next one's a positive, positive, positive. Yeah, the next one's a positive. I, x to the 9th over 9 factorial plus dot, dot, dot. Okay. So now what I'm going to do is I'm going to group these. I'm going to group these with terms that have I in them and terms that don't have I in them. So this is going to be equal to 1 minus x squared over 2 factorial, okay, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. So I did this one, this one, this one, this one, this one, right? Plus x to the 8 over 8 factorial plus dot, dot, dot. I'm going to do that. Plus, now everyone that has an I in it, is left over. So what I'm going to do is I'm going to factor out that I. I'm going to go I times, okay, I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, okay, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Okay. Oh, and that should be a dot, dot, dot. Okay, these are going to go on forever as well. Okay, plus dot, 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 dot. Okay, those are going to go on forever as well. Okay. And so what we're going to get here, okay, is what? What was this guy? What were the odds? What were the odds? What did we say the odds were? I'm sorry, the evens. What was the evens alternating? We just arrived at that, right? What's this first power series? Very good. It's cosine of x. So this is cosine of x plus I, and then the second one was sine, right? I sine of x. And this is called Euler's formula. E to the I x is equal to cosine of x plus I sine of x. That's where we get that formula in trig. Okay, when we talk about, okay, this is Euler's formula. Okay, Euler's formula. It's amazing formula. Okay, and so e to the ix, now what would happen if I plugged in pi in here? I would get e to the I pi is equal to the cosine of pi plus I sine of pi. I sine of pi. Well, what's the cosine of pi? Well, it's -1. What's the sine of pi? It's 0. So this thing goes to 0. And so we get e to the I pi is equal to -1. If I bring the -1 to the other side, I get the extremely famous identity called Euler's identity. E to the I pi plus 1 is equal to 0. And in this one identity, this is an identity, okay, Euler's identity. In this one identity, we have the 5 most used symbols in all of mathematics. 5 most used symbols in all of mathematics. We have e to the I pi plus 1 is equal to 0, which is incredible. Okay, that's just amazing. And then the universe, in the universe, there was much rejoicing. Okay, e to the I pi plus 1 is equal to 0. Okay, Euler's identity. Nice, nice, nice. Okay, let's derive another famous formula. Okay, let's derive another famous formula here. Okay, and then we'll probably call it a day. Okay. Okay. What did we do? This was Euler's formula. I'm going to call this number 4. Call this number 4, and then we're going to move on to number 5. What was the other one, number 4? I don't remember. Oh, no, that was 4. So this is 5, and then the next one is 6. Okay, and then, okay, we'll say this one is 6. Okay, so find the Maclaurin series for k f of x is equal to 1 plus x 1 plus x to the kth power. Okay, we want the Maclaurin series for this thing. Okay, so we've got to, okay, what's the Maclaurin series? F of x is equal to f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus dot, 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 dot. Okay, so this is another famous formula. Okay, extremely famous formula we're gonna derive with power series. Okay. Extremely famous. Why? Because this is called a binomial. Okay, 1 plus x to the kth power. I'm going to see what happens with this guy. Okay, so yeah. Okay, you could think of it as x plus 1 to the kth power. Doesn't matter. Okay, so we're going to expand this thing. Okay, so we want f of x is equal to 1 plus x to the kth power. Okay, and then evaluate that at 0. F of 0, what's this going to become? This is just going to become 1 to the kth power, which is 1. Okay, anything to the 1 to any power is 1. Okay, what about f prime of x? This is going to be k times 1 plus x to the k minus 1. Right? So what's f prime of 0? Well, this is just going to become k times 1. Right? K times 1, which is just k. Okay. Okay, what's f triple prime of x? This is k times k minus 1. K minus 1 times 1 plus x to the k minus 2. So what's f double prime? This is a double prime, not triple prime. Okay, what's f double prime of 0? That's just k times k minus 1. Okay, cool, cool, cool. Okay, what's f triple prime of x? That's k times k minus 1 times k minus 2 times 1 plus x to the k minus 3, which is f triple prime of 0. Okay, remember this thing always goes to 1. So that's just going to be equal to k times k minus 1 times k minus 2. Come on. Come back to me, please. Are we good? Are we not good? Let me stop my sharing real quick. Is this freezing? What's going on here? Okay. Task manager. Where's my task manager? OneNote. Let's end the task. I will end you. You are ended. Okay. I will literally end you. Okay. Okay. So k times k minus 1, k minus 2, f triple prime of 0. Okay. Oh, sorry. This was times 1 plus x to the k minus 3. So f triple prime of 0 is equal to k times k minus 1 times k minus 2. Okay, so you can kind of see what's happening here. Every time I'm multiplying by, you know, one more value less than the previous one. Okay, so I start with k and then I go k minus 1, then k minus 2. Okay, so what would the nth derivative be here? What would the nth derivative be? Well, the nth derivative, okay, would be k times k minus 1 times k minus 2 dot all the way to, right? So for the third, it was the second. So what I'd really want to do is I would want to do k minus n plus 1. I think that's right. Is that right? Is it? Because for the third derivative, no, it's k minus n minus 1. K minus n minus 1. Because if I wanted the third derivative, I stop at 2. Yes. If I wanted the fourth derivative, I stop at 3. If I wanted the fifth derivative, I stop at, yes. So this is it. Okay, k minus n minus 1, right? Okay, so that's the nth derivative of this thing. Okay, so let's put all the pieces together here. Okay, so, right, so, and then this would be 1 plus x to the k minus n minus 1 degree. Okay, if we plugged in 0 here, okay, this thing would go to 1, so I'd just be left with this. Okay, so hopefully that makes sense. Okay, so 1 plus x to the kth power is going to be equal to 1, okay, plus k times x plus k times k minus 1, k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 all over 3 factorial x cubed plus plus, okay, this is going to be k times k minus 1 times k minus 2 okay, all the way down to k, I'm going to distribute this minus sign, k minus n plus 1 all over n factorial times x to the nth plus, and then this is just going to keep going on forever. So I'm just saying, you know, for the nth factorial, this is okay, what it's going to look like. Okay, so this thing, however, that thing right there has a special formula. Oh, okay. So that thing actually has a special formula, and this comes to us from, well, how would I get k times k minus 1 times k minus 2? How would I get that? If I like think in terms of factorials, right? A factorial here. Well, wouldn't this be, say, k, right? K factorial over, say, 2 factorial, wouldn't, right? Because, or no, sorry, this would be not 2 factorial, because I'm not getting off 2. It would be k minus 3 factorial, I want to say. K minus n factorial. So k minus n, let's see if this works. K minus n factorial. Does that work? Okay, k factorial over, so if I wanted to get k over k minus 2 factorial, okay, so that would give me k times k, yeah, this works. Okay, so if n is 2, well, let's think about it this way. Okay, let's think about it this way first. K times k minus 1 times k minus 2. What would I have to do with this one? This one, I would have to have this. I would have to have k factorial over k minus 3 factorial. Why? Because I would want the k minus 3 factorial to cancel out everything after k minus 2. Does that make sense? I would want the k minus 3 to cancel everything out after k minus 2. So this equals that, k factorial over k minus, say, 3 factorial. Okay. So in a way, this would be k minus n plus 1, which is exactly what we have as our last term here. Okay, factorial. That's equal to this thing, right? So that's going to give us our previous one. So I don't know if I'm explaining this real well, but this gives us k times k minus 1 times k minus 2 dot 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 all the way up to k minus n times k minus n, because I would get rid of the k minus n plus 1. Okay, k minus n. Oh, you know what? Did I screw up? Minus, yeah, I did. This should be in parentheses. K minus n plus 1. Okay, for that guy there. Boom. Okay, k minus n plus 1 factorial. That's going to give me that thing on the top. Okay. So if I don't want to cancel out if I want to go all the way to n plus 1, though, if I want to do k minus n plus 1, okay, then think of it this way. We would go all the way down to k minus n plus 1. The next one would be k minus n. And so what I'd have to do is I would have to cancel out the k minus n factorial, because this is actually the one above it. This k minus n plus 1 is the one above it. Above k, it's one above k minus n. Think of, maybe numbers will help, right? When we get too many variables, we really want numbers to help us. So think of this as k minus 5 plus 1. What is that really? Isn't that really k minus 4? And so what would I want? I would want k minus 5 to factorial to cancel everything from then down, right? We would want k minus 5, right, to cancel anything from, so k minus n factorial, we'd want that to cancel anything down. And so that just becomes n factorial times k minus n factorial to get this whole thing, the whole thing there. All of that is a formula already that we have from probability. This is what it is. Okay, it's all to say that we have this formula from probability already. That is k factorial over k minus n factorial times n factorial. And this is out of k items, choose n of them. Out of k items, choose n. That's out of k items, choose n. Okay, or we sometimes write it like this. Out of k items, choose n. Okay, and that's going to give us our coefficients for these values. Okay, and so how would I write this out? 1 plus x to the kth power, okay, is going to be equal to, okay, this is the 1 plus kx, right, plus k times k minus 1 over 2 factorial, okay, x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus dot, right, forever. Okay, but what are these in terms of this formula? Well, we could rewrite this as the summation as n equals 0 to infinity of k choose n, out of k items choose n of them, okay, times x to the nth power. Okay, for example, this would be out of k items, right? Out of k items, if it was, okay, if k was say 2, right? So let's do an example with just numbers. Okay, so this is 1 plus x to the 8th power, and this is called the binomial expansion theorem. Binomial expansion theorem. Okay, from probability, binomial expansion theorem. Okay, so, and it's Pascal's triangle right here. Okay, this is how we get Pascal's triangle. So we say, okay, so 1 plus x to the squared is equal to, we're going to binomial expand this, right? So well, this one's easy. This we could do by hand. 1 plus 2x plus x squared, right? Wouldn't that be 1 plus 2x plus x squared? Yeah, it's just totally easy. Okay, fine. Okay, so this is going to be, but how would we do that using the summation? This would be out of, what's k? It's out of 2, choose 0, times x to the 0 power, plus out of 2, choose 1, times x to the first power, plus out of 2, choose 2, x to the second power. Okay, well, how many ways can you choose 0 out of 2? Well, that's one way. What's x to the 0? That's 1, so we get 1. Out of 2, choose 1. How many ways can you choose 1 out of 2 items? If you want apple pie or pumpkin pie, you're gonna have to choose. You have to choose one of them. What's the only way that you can choose one? There's 2 ways. 2x plus out of 2, choose 2. How many ways can you choose both? Just 1. You choose both. So that's 1x squared. Boom. Okay. Let's try one that's a little bit more difficult. What about 1 plus x to the 5th power? Right? What's 1 plus x to the 5th power? Well, according to Pascal's triangle, this would be 1 plus, what would this be? This would be 10, let me think about this for a second. This would be 1, 5, 6, 4, 4, 4, 6, and 5, and 1, I think. Is that right? So 1, 2, 3, 4, 5, 6, 7, 8 terms. I don't think that's right. I think I'm missing something. Okay. At any rate. Okay. Again, real easy to do. Let's just plug it in. Okay. Maybe there's too many terms there. think there was too many terms. Let's just plug it in. Okay, what's this going to be? It's going to be out of 5, choose 0. Okay, x to the 0, plus out of 5, choose 1, x to the first, plus out of 5, choose 2, x to the second, plus out of 5, choose 3, x to the third, plus out of 5, choose 4, x to the fourth, plus out of 5, choose 5, x to the fifth. Okay, so 1, 2, 3, 4, 5. Yeah, I should have only had 6 terms. Okay, so how many ways can you choose 0? One way. So this is just 1. Okay, 1. Come on, stop. Be nice. Almost done. 1 plus, how many ways can you choose 1 out of 5? 5. Okay, that's x. Okay, how many ways can you choose 5 out of 2? This is going to be 5 factorial over 2 factorial, so we get rid of 2. That's 5, 4, 3. Minus 5 minus 2, that's 3 factorial, so we're going to get 6. So that's going to be 5, 4, 3. 5 times 4 times 3 is 60 divided, that's 10. Okay, 10x squared plus, and what's nice is there's symmetry here, so this actually goes 1, 5, 10, 10, 5, 1. Boom. And again, we would get this by Pascal's triangle, right? Remember that Pascal's triangle? It would be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. That's where I got that 4s and 6. I was way off. 1, 5, 10, 10, 5, and 1. This would be for 1 plus x to the 5th power. This gives me my coefficients. Boom, done. That's the binomial expansion theorem. Boom, done. We proved it using power series. That's it. That's it for today. Okay, a lot of powerful mathematics today. And we just have 11 tomorrow. Review on Monday. Hopefully everybody got my whatchamacallit. Hopefully everybody got the study guide. Okay, could you post a recording, Brazil? Yes, absolutely. Okay, I will do that, convert it. It may take 3 hours to convert, but tomorrow I won't have that problem. So, yeah. Okay, I will chat with you guys tomorrow. Okay.